crosstalk or near field coupling, module 4.4. In this module, we will investigate crosstalk to shielded wires. We will be using low frequency analysis. There are many different types of shielded cables that we use very commonly. There can be signal cables or power cables. The analysis presented here are applicable for all these cables. But however, for simplicity, we will be concentrating on a single core shielded wire cable as shown here. Now, this is the generic situation that we will analyze. So this is a shielded cable, single core, and that is represented over here. It has got a central core which we call as a receptor wire and the cable shield, and you can have a connection to the ground through a resistor at both ends. So this is the near end where the source is also coming in the generator wire. So generator wire is external to this shielded cable, maybe something parallel to this cable. And the far end is away from this generator, resistor RF. So for the shield to work, both ends of the shield has to be connected. So in that case, there can be a current also to the shield. Then VG represent the voltage between the ground and the generator wire. So Vs is the source voltage. So VG will be equivalent to like V12 that we have seen before, the voltage difference between the generator wire and the receptor wire. The generic models for inductive coupling and capacitive coupling we have seen before. So these principles we will be using in this analysis, and as before, the inductive coupling is V equals minus M di2 by dt, and capacitive coupling source ICT is C12 dV2 by dt. And similarly, the parallel capacitance to ground can be neglected if this condition is true, and the series inductive impedance can be ignored if this condition is true. All these are valid in this analysis also, but there will be some modifications for that due to the presence of the shield. Now let us take this situation and find the equivalent circuit for analysis of capacitive crosstalk and equivalent circuit for the inductive crosstalk. So we have a capacitance between the generator wire and the receptor. So we can draw it like that. Well, it is not a very good drawing, but something like this, and you have something similar between the receptor wire and the cable shield. So they are shown here. So this part is this source circuit, and CGS to the shield. So this is the shield point. Then CRS between the receptor wire and the shield. So that is this capacitance. Then this part is the receptor circuit, RN and RF. So while drawing this, now we assume that okay, the shield is not connected to be more general. So if the shield is connected, then of course you have a connections directly like this, and this is short circuited, and you eliminate the capacitive coupling. So this parallel combination of CGS and CRS is similar to this capacitive coupling capacitance C12. So that is the only difference in the model. Now let us look at the model for the inductive coupling in the case of a shield. So this is much more complicated than before, and instead of one circuit, one voltage source, you will find that there are 3 voltage sources. Let us see how it is coming. Now take the current in this. So this current will create a flux linkage both with the receptor circuit as well as the cable shield, and direction of those magnetic field you can represent as it is going into the paper. So something like this. Now since this generator wire is further away and shield and cable, receptor and cable shield are so close to each other, basically it is the same flux that is linking with both receptor circuit and the shield circuit. Now we assume that the shield is connected at both ends for the generic case, whereas here it is open for the generic case. Now MGR is the mutual inductance between the generator wire and the receptor wire. So that is the source, j omega MGR Ig. So this source is coming in the receptor circuit, and it will drive a current in such a way that it should create a flux opposing this. So that flux is coming out of the paper. So you will have a flux coming out of that paper like that only if the direction of the current is in this way, from here to here. So the polarity is like this. So this will drive a current to oppose the original flux. So that is one source. Now a similar source will be there in the shield circuit also. So you take the mutual inductance between the generator and the shield, MGS. So it is this source. Now since we don't have any deliberate resistors in the shield, so you cannot neglect the series resistance and series inductance of the shield, self-inductance of the shield. It cannot be neglected because otherwise it is short circuit. So that is that need to be included in the shield circuit. So this will be your shield circuit with the source. Now this source will be driving a current, shield current IS, and this is a fairly substantial current, and this current will create, this current will create a magnetic field that will be coupling with the receptor circuit. Now that the polarity of that will be in such a way that it will be opposing this flux shown here. So that is shown here, that source. So it is j omega mutual inductance between receptor and the shield, between the receptor and the shield, times IS, the shield current. So you have two opposing sources in the receptor circuit, and immediately you can see that this opposing sources will reduce the general circulating current in the receptor circuit, and that is how the shield is working in reducing the noise voltages Vn and Vf. So a necessary condition for that is that this has to be connected at both ends and there has to be a circulating current. So this gives the complete equivalent circuit for the inductive coupling. Now we can do further simplifications in this. Say for example, if you take the mutual inductance between generator wire and the shield, that will be approximately equal to between the generator wire and the receptor also. So MGR and MGS, so these two sources are almost identical. And similarly MRS, mutual inductance between the receptor and the cable shield, since they share the same area, that will be equal to the cable self inductance LS. So MRS can be replaced by this LS. So those simplifications we will see next. So first, before that, let us go further into the capacitive coupling. We have seen that a combination of these two is equivalent to C12, the coupling capacitance, in the absence that shield is not connected to the ground. So series capacitance is equivalent, capacitance is like a parallel combination. Then VF equals Vn. You can write it like this, where C12 is given by this. So total coupling capacitance between generator and receptor. Now CRS between the receptor and shield, this is much larger capacitor than this one. So often we are able to neglect this and keep only this one, CGS. So basically then it will be as if there is no shield present, only CGS is present in the case when they are not connected to the ground. So the current in the generator circuit IG, under the assumption of V coupling between them, we can write it as Vs by Rs plus RL. So substituting that in the previous expression, you get this one. Then you make simplification. Vs Vg, in terms of Vg, you find Vg equal to RL by Rs plus RL Vs. So where Vg is generator wire low frequency voltage. Now our expressions have reduced to one similar to the capacitive coupling between the two wires. So Vg in our case is similar to V12 in the previous case, and C12, which is this one, is approximately equal to CGS or CGR. So this Rs can be neglected within that. If the shield is connected, then Vn cap or the capacitive crosstalk will be 0 as before. So this can be represented in this way. So this is a plot of frequency versus capacitive crosstalk, and in the case of capacitive crosstalk, near end crosstalk is always equal to far end crosstalk, irrespective of the impedances at near end and far end. So when the shield is not connected to the ground, even at one end, then we have this expression. So you can see that it is changing with j omega. So it is 20 dB per decade change. So this is a shield not connected to the ground, or it is equivalent to having no shield at all. So when the shield is grounded at both ends, or even at one end, this is applicable even for connection to one end, then suddenly it becomes 0. For capacitive crosstalk control, you need to connect the shield to ground only at one end. Both ends need to be connected for inductive crosstalk elimination or reduction. Now coming to inductive coupling. Now the equivalent circuit is shown here. We have derived that before. Now the shield current can be written as j omega mgs ig by Rs plus Ls. Then this Vn induced can be written as from the circuit analysis from these two sources. You can write it like this, where Is is given by this expression that can be substituted over here. Then you get an expression like this. Now, as said before, you can see that this loop area for the receptor circuit and the shield circuit, they are almost similar. So MGS and MGR, they are more or less equal. Similarly, mutual inductance between receptor and cable shield, MRS, is approximately equal to the cable self-inductance. So with these two simplifications in the previous equation, we can write the expression like this. So here there are two terms that are a function of frequency. One is this and another one is this one, with two factors. So now if you are increasing the frequency from very low value and rising it up, what will happen? We can see that. So this part is crosstalk with no shield at all, or shield open circuited, and this part comes only when there is a shield current or when there is a shield. So this is the modification of the crosstalk due to this. So immediately from this equation you can see that the reduction of crosstalk is a function of the shield properties and the frequency. Rs is the resistance of the shield, Ls is the self-inductance of the shield. So the shield properties and frequency decides how much beneficial effect the shield will have in the inductive crosstalk. So this is the effect of the shield. So at very low frequency you can find that this will be almost equal to 1, because this part will be very small compared to this part. So this ratio will become 1. So there is no effect of the shield. Only after certain frequency, you can see from this equation, the shield will have an effect. And that turnaround frequency is given by when Rs is equal to omega Ls. So this is what we will see next. The expression for the near end crosstalk and expression for the far end crosstalk due to the magnetic fields. So this part is the shielding factor, Rs by Rs plus j omega Ls. Now dividing numerator and denominator by Rs, we define a new term, a time constant Ls by Rs, shield time constant it is called, which is a property of the shield. So we write it as 1 by 1 plus j omega tau s. Now the shielding factor will be 1 if omega tau s is less than 1 approximately, and this will be equal to Rs by j omega Ls, or 1 by j omega tau s if omega tau s is greater than 1. So this 1 can be neglected, then it is 1 by j omega tau s, which is nothing but Rs by j omega Ls. So corresponding to omega tau s is equal to 1, we get a frequency which is called the cutoff frequency as 1 by 2 pi tau s is equal to Rs by 2 pi Ls. So below this frequency there is no effect of the shield, and above that frequency you will have a shielding effect. So how do we represent that? What does it mean? So below omega less than 1 by tau s, so below that frequency, this Ig returns via the ground. It is not going via the shield. Whereas above that frequency, Ig is returning through the shield, and Is is equal to Ig. Then substituting those values, we get near end crosstalk and far end crosstalk by this expression Vs by Rs plus Rl. So this is only when omega is far greater than 1 by tau s, this expression is valid. So below that shield cutoff frequency, it is 20 dB per decade increase. Where shielding factor is 1, so it is just j omega mgrig, j omega mgrig here. Now above the shield cutoff frequency, it becomes Rs plus j omega Ls. So this j omega and j omega cancels. So you get a kind of a saturation in the induced voltage. So it is not frequency dependent anymore beyond that cutoff. So for RG58C cable, the shield cutoff frequency, we can find it is about 2 kHz. So what does it mean? It means that below 2 kHz, this particular cable will not be helpful in preventing inductive crosstalk, whereas above 2 kHz, it can prevent or it can reduce the inductive crosstalk. So conclusions: to eliminate capacitive crosstalk, the shield should be connected to ground at least at one end, and to eliminate inductive crosstalk, the shield should be connected at both ends to drive a shield current. In that case, a shield with a low resistance Rs and a large inductance Ls is good for reducing inductive crosstalk. So this comes from, say, shield cutoff frequency. Low resistance and large inductance means F0 becomes smaller. So it means that even from very low frequency, you will have the effect of the shield. Below the shield cutoff frequency, the return currents are via the ground, no shielding effect from magnetic field, and above the shield cutoff frequency, the return currents are via the shield, shielding from magnetic field. So here we have shown a very important principle also, because often AC currents return via a path that will minimize the flux. So it's a general principle. So it is not, it may look like that the current will be following always through the reference because you have some inductance and resistance. But that is not the case with AC currents. So the flux minimization principle is valid. So this will have a lot of practical consequences. I mean, here we are doing this analysis in terms of a cable shield. But you can have other conditions also. Say for example, in electrified railways, you have high frequency components superimposed on the traction currents, and the rail is supposed to be the return path in that case. But often the high frequency currents may return not via the rails but via the wagons, and it may damage even the bearings because of that currents. So in AC, the return currents, the currents would like to return through a path where the flux is, the coupling flux is minimized. Now, shielding can also be used to prevent radiated emission. So here it is illustrated here. So far we have been seeing how shielding can prevent noise pickup from outside. Now here it is shown how it can be used to prevent emission. So in this case the cross section is shown. A bare conductor, no shield, then you have magnetic field and electric field freely transmitted to the space surroundings. Now suppose you have a shield and at least one end of the shield is connected to the ground, then all the electric field lines are terminating on the shield, so you don't have any electric field emission, but you still have magnetic field emission. So shield current is 0, even though the generator current, here the generator is now this inside conductor, that is not 0. Now if the shield is connected at both ends, it will drive a current through the shield, so the shield current is not 0 anymore, which will confine all the magnetic field to the inside of the cable. So when shield is grounded at both ends, it will prevent radiated emission. So some more detailed analysis. So you have a source. Now the source is connected to the inner conductor, so the load here. So the current has, the shield is connected at both ends. The current can return either via the ground like this or via the shield current. Now this, you can find an equivalent circuit for this. It is as if you have an inductive coupling between the inner wire and the shield. So LG and L as such. So you have this mutual coupling also between them, LGS. So you write the loop equations. So this is the shield current IS, J omega LSH plus RSH minus a source created in this IG J omega LGS. So from that you can find what is the value for IS. Then shield constant is LSH by RSH, and I0 is the sum of this IG and IS. So the difference actually is what is flowing through the ground. So I0 by IG is same as the shielding factor, and that is equal to 1 by 1 plus j omega tau s. This you can find from this expression here. Then which will be equal to 1 for omega far less than 1 by tau s, and RSH by j omega LSH for omega greater than 1 by tau s. So very similar kind of equations you get when you analyze the shield to prevent radiated emission. So that is end of that particular module on shielded cables, crosstalk in the presence of shielded cables. Thank you.